if we have a function f of x, we know that we can differentiate. I'm just going to write diff for differentiate. We know we can differentiate that function and get a derivative f prime of x, so long as it's a differentiable function. We've seen situations where functions might not be differentiable everywhere, but let's not worry about that. Let's just pretend that it is. It is a function. We can differentiate it, and we get the derivative f prime of x. Now, that is also a function, and it might also be a differentiable function, in which case we could decide to differentiate that again, and we would get what we call the second derivative, f. I've heard this called f biz a long time ago. Usually we just say the second derivative, but it's got two of those little prime symbols. This is the second derivative, and it is also a function, and it might be a differentiable function, so we might be able to differentiate that to get the third derivative, and we might be able to continue and get the fourth derivative. Once we get up to the fourth derivative, we stop writing those little prime markers, and we just put the number of the derivative in parentheses. And we probably can continue on. Sometimes you get to a point where the second derivative or the third derivative or the fourth derivative is just 0, in which case all of the subsequent derivatives are going to be 0, because when we have a constant function, the derivative of that is 0. And so, anyways, it's not going to necessarily be that all of these are unique non-zero functions, but if we continue getting functions that are then differentiable, we can continue differentiating and getting higher derivatives. All right. We can also look at the Leibniz notation. So if we have y as a function of x, if we differentiate that, we can write that as dy over dx. That's the derivative of y with respect to x. If we differentiate that again, we write this as d squared y over dx squared. I know that might seem a little bit weird, but we are differentiating twice, and it's with respect to x both times. In Calc 3, if you're going to move on to Calc 3 eventually, you're going to see situations where we might differentiate with respect to one variable and then later with respect to another variable when we have functions of multiple variables. Just that's something that's not for today, but kind of a reason for why we might be writing these things a little bit complicated. If we want the third derivative, that's d with a 3y over dx cubed, and for the fourth, it's the same. It's d to the fourth y over dx to the fourth. It's not really the same as, we're not really raising d to a power. It's where we're taking the derivative so many times, but we use the same notation that we would use as exponents. So we can, if our function is differentiable, and then the derivative is differentiable, and then the derivative of that is differentiable, we can keep taking derivatives of these subsequent functions and getting higher and higher derivatives. Let's take a look at just a mathematical example, and then I want to talk about one way that we can interpret these higher derivatives. So let's take a look at the function f of x equals x cubed, and let's find the second derivative of x, the third derivative of x, and the fourth derivative of x. So to find the second derivative, we first need to find the first derivative. So f prime of x is going to be the limit as h approaches 0 of x plus h cubed minus x cubed over h. I do not want to spend time going through and doing the whole calculation for expanding that binomial cubed. So I'm just going to give you what we get there. And if you really want to do it, you can do it on your own. This is going to be x cubed plus 3x squared h plus 3xh squared plus h cubed minus that x cubed, still all over h. Now we do have a little bit of cancellation that's going to happen. The x cubes are going to cancel because we've got a positive x cubed and a negative x cubed. And then what we can do is we can take each of those terms that are left and we can divide them by h. So we still have the limit as h approaches 0. But when we divide all of those terms, we're going to get 3x squared plus 3xh, because h squared divided by h is h, and then plus h squared. And if we're looking at the limit as h approaches 0, those last two terms are going to equal 0 when we plug in 0 for h. And so what we're left with is just that first term, 3x squared. So that is the first derivative. If we want the second derivative, we are going to have to take the derivative of what we've already gotten. So it's still going to be the limit as h approaches 0, but when we're plugging in our function, because the second derivative is the derivative of the first derivative, we're going to use 3x squared for the function that we plug in here. So this is going to be 3 times x plus h squared minus 3x squared all over h. Now we can go and expand that first part of the numerator out. It's going to be a perfect trinomial square. We're going to have to multiply that by 3. I'm just going to do all this in one go. It's going to be 3x squared plus 6xh plus 3h squared, and then minus that 3x squared that was there. It's because when we take x plus h squared, we get x squared plus 2xh plus h squared. Then we've got to multiply all those by 3. So that changes those coefficients. Now we've got a little bit of canceling we can do. The positive and negative 3x squared are going to go away because when we add those together, we get 0. And then we've got two terms left that both are divisible by h. So let's divide those by h. 6xh divided by h is going to be 6x, plus 3h squared divided by h is 3h. And the limit there is h goes to 0. That second term is going to vanish, and we're just going to have 6x. So the first derivative was 3x squared. The second derivative is 6x. To find the third derivative, we're going to have to go and differentiate 6x, which means we're still going to be using this limit definition, but we're going to be using 6x as the function that we plug things in here. So if we look at that function when we plug in x plus h, this is going to be 6 times x plus h minus 6x over h. All right, I don't want to write out too much here. When we distribute this 6, we're going to have a positive 6x and a negative 6x. Those cancel, and we're just going to be left with this 6h. So let's do all of that in one step. We've got the limit as h approaches 0 of 6h over h. We can divide those h's, and then we've got the limit as h approaches 0 of 6. And that is just going to be 6. The limit of a constant is that constant. So our third derivative is 6. Oh boy. Let's do one more. The fourth derivative. If we want the fourth derivative, we need to take the derivative of the third derivative, which is the derivative of 6. We can use the limit definition. We can also use what we know that graph is going to look like. Some of you might already be able to tell. This is a constant function. It is a horizontal line. That has slope 0, so our derivative is going to be 0, but let's deal with it anyways. Our function is 6. When we evaluate that, it doesn't matter if we're evaluating it at x plus h or if we're evaluating it at x. The function value is always going to be 6, so that's going to be 6 minus 6 over h. And 6 minus 6 is 0, and 0 divided by anything other than 0 is going to be 0. But remember, we don't want to look at this when h is equal to 0. We just want to look at values near 0. And so 0 divided by anything near 0, but not equal to 0, is going to be 0. And of course, the limit of 0 as h approaches 0 is just 0. So the fourth derivative is 0. In fact, if we wanted the fifth derivative, again, this is a constant function. The derivative of a constant function is 0. So we know that the fifth derivative is going to be 0. Same thing with the sixth derivative, the seventh derivative, etc. Now, I would love to take the time to look at an example of what these things mean with respect to the position function, but this video is already too long, so I don't want to go through a whole example. We will do, if you look through the list of worked out example problems, there is going to be one there. But one quick note, if we start with a position function and we take the derivative, that gives us the velocity function. We've talked about that before. We know that we took the derivative to figure out instantaneous velocity, but if we take the derivative of a position function, that gives us a velocity function as a function of time. If we take the derivative of that, we end up with the acceleration function. So the second derivative of a position function gives us acceleration, and the third derivative actually gives us something called jerk. It is an idea in physics, and it's named jerk because if you have a large jerk, it's a sudden change in acceleration, and it would feel like your body is being jerked around. Like if you're on a roller coaster and it accelerates really quickly, you get that, painful sort of a sensation. Anyways, there is a worked out example problem that does go through acceleration and velocity and all of that. So please take a look at that just to make sure you've got an idea of how that works.